Hello everyone, welcome to this episode. In this episode, I want to talk about the group actions. Group action is a very important and useful concept in group theory. By learning the group actions, you can understand how does the elements of groups permute or be the symmetric of the elements in a set. So it will help you to deeply understand the concept of groups. And group actions is related to several different areas of the group theory. So we cannot finish the talk about the group actions in just one episode. So in this episode, I will just give you a very short or brief introduction to the group actions, and then in the future episodes, we will spend some time to talk about the different aspects of group actions in detail. So let's begin. At first, let's look at the definition for the group actions. It says that a group action of a group G, so you should have a group G to define this group action. Then the group G is on a set A. Then this group action is a map from the direct product of G and A to the set A. So it means that you need to have a group G and a set A. The group action is defined up on the group G, and the action is act on the set A. So this is the concept of group action, and this action is a map, and this map maps the element from G direct product with A, in which if we consider the elements G from the capital G and A from capital A, so G is the group element and A is the element of the set. Then we just map G, the ordered pair G and A, which is the element of this direct product, to some element, maybe A prime, in the set A. So this is the map of the group action. And sometimes we just write this action by G dot A to denote this ordered pair. And because this map this ordered pair to A prime, so for this notation we just mean that G dot A we just let it to equal A prime. And the reason why we use this notation is to show that we use the element small g to act on one element of the set A, which is this small a, we get another element A prime. So this is the group action. Okay, and this map is not just like any map. It should satisfy the following two properties here. For the first property, this property, we need to have if we use the group element G2 to act on one element A in the set A, then we use G1 to act on the result of the first action. It is equal to, if we do the like a G1 times G2, which it may not be the product, or like a multiplication, but the group action, group of group operation between G1 and G2, then because this operation is in the group G, so we will get some another element in the group G, and that element act on A. So those two parts are the same. So another way to say that is that the left hand side means that because for the action like a G2 dot A, G2 dot A is action to action of G2 from the group act on the element A, we should get something maybe A prime in the set A. This is equivalent to say that G2 is a map to map the element A to another element in the set capital A, which is A prime. So the group action is actually can be seen as the map. Then the left side of this equality, G1 dot G2 dot A, is equal to G1 dot the image of A under the map of G2, which is equal to, because this G1 action is also can be seen as a map, so this is G1 map maps the result of G2A like this, and this is equal to G1 composite with G2 when we consider G1 and G2 are maps and apply to the element A. So this is the left hand side we get, and the right hand side is G1, G2 act on A, and this is equal to if this G1 operation with G2 is equal to some group element G3 in the group G, then we get G3 act on A, which is G3A, and because those two should be the same, we get G1 composite G2 equals G3 when we consider them as maps. So because G3 in the group is G1 times G2, then this means that the composition of the group elements when we consider them as maps is equal to the multiplication of the group elements. So simply speaking, this first requirement require us to have the group elements to have the property that the group action between elements is equivalent to the composition of those elements when we consider them as maps. Okay, this is the first property. And for the second property, it says that 1 dot A equals to 1, and this 1 is the identity element of the group G. So it means that the identity element in the group G act on any element in the set A. It just you get the A back. So the identity element gives identity map. This is the second property. Okay, so now we know what's the definition of group actions. Let's look at some examples. So for the first example, which is the most simple group action, is the trivial group action. So trivial action. So for its name, we can see that this action just trivially map the element of the set to itself. So trivially map just means the map is identity map. So this means for any group element G in the set G in the group G, and any element A in the set A, then we define G dot A should equals to A. So any element of the group is the identity map for this set A. This is the trivial action, and we want to show that this action is actually a group action. We need to check that this map, this action satisfies those two properties in the definition. So first we want to show the first equality is true. So that means if we have G1, G2 in the group G, then G1 apply to G2 apply to A is equal to here for the G2 act on the element A, and because of this definition trivial map of the action, we should get the result is A itself. So this will give us G1 act on A because this part is equal to A itself. And similarly, this is also an element of G act on the element of A. We should this is the identity map because of this definition for trivial action. So we will get A here. Then for this equality, we need to consider the right hand side. So this is G1 multiply G2 act on the element A. Because G1 and G2 under the operation of the group, we get some like another element in the group. We can call it G3. So this will become G3 act on A. And because G3 also one element of the group, so when we act on A, it is the identity map, we get A back. And here this one equals this one, so this one equals to each other, and it tells us that G1 dot G2 dot A, which is this part, equals to this part, G1 G2 dot A. And this is the first property we want to verify. Okay, and for the second one, for the identity element 1, we call it 1G dot any element A from the set A in capital A. This because the identity element is also one element of the group G, so it should satisfy this trivial map property as well. So it means that this action gives us A itself, and this immediately the second property we want for the group action. So we can see that the two properties of group actions are satisfied. So this trivial action divided by this is group action. So this is a group action. Checked. Now let's look at a more advanced example. So this example is the group action of the symmetric group SA on the set A. And here, this notation means this is the symmetric group over the set A, and this is equal to Sn for where n is equal to the cardinality of the set A, which means the number of elements in this set A. And sometimes we are using this notation instead of this one, Sn, which the subscript is the number, but we can use this notation in which the subscript is the notation of the of a set. In this case, it means that the elements in this symmetric group SA are considered to be the permutations of the elements specifically over this set A. Although it is isomorphic or equivalent to this Sn, but in this notation we know that we just want the permutations to be the permutations over this set A. So this is the different notation. Okay, and then we define the group action for any maybe sigma in the symmetric group SA, and any element A in the set A. We define the group action, not G, the sigma dot A, sigma act on the element A is equal to sigma permute the element A. So this is the group action, and we want to prove that this group action is actually a group action, satisfies those two properties. So that is one. We want to show that for any sigma 1, sigma 2 in SA, we have sigma 1 act on the result of sigma 2 act on the element A, and this because of this definition, the permutation sigma 2 act on A means we permute this A by the sigma 2. This is out. Okay, and this one also equals to sigma 1 act on sigma 2 permute A. So we get this one. So then, because the permutations are bijection maps, so this format just means that we have a composition of sigma 1 and sigma 2, and it map A to some element in another element A in the capital A, and here, and this again equals to sigma 1 composite with sigma 2 act on A because of this equation, which defines this group action. Okay, we get this, and here, because for the symmetric group SA, the elements are the permutations, and the permutations are maps. So the operation in the symmetric group is the composition between maps. So that is so this part just is the operation between the two elements of SA, and if we just write the operation in the symmetric group as a multiplication, this is equivalent to sigma 1 times sigma 2 and act on A. and this is what we want, for the first property of the group action. Okay, so the first property is checked, and then second one is that we want to show that the identity element maps any element in the set A to itself. So we say that sigma 0 is the identity permutation in symmetric group SA. And as we know, the identity permutation is the permutation does not permute any element in the set A. So in this way, sigma 0 act on any element A means it maps A to another element, and because sigma 0 does not permute any element, so it fixes A. So we get A here, and this is what we want for the second property. Next, let's look at some properties of the group action. And before we are doing that, let's define a map for the group action when we fix some elements in the group. So here, if we have the group G, which is act on the set A, and we fix one element G in the group, we can define a map sigma G by this, the map A to itself, and the sigma G map A is equal to the element G act on the element A, which this A is any element in the set capital A. And this map is group action, like in a special notation, because here we just fix one element in the group G. So like this group G, this element small g defines this map sigma G, and for different elements in the group capital G, we will have a different maps like this. So be careful here, we only fix one element from the group G. And recall the definition of group action. It is a map from G direct product with the set A maps to the set A like this. This is the group action, and it just maps some G and like the ordered pair GA to something A prime in the set A. And here, because in this map we are fixing the element G, we fix this element G. So in the group action, this G is fixed, and we only change the element of A and map it to different elements in A. So it is equivalent to say that we can just ignore this element in the group G when we consider the map. That is equivalent to say we map some element in the set capital A to capital A itself, and this is why we have this definition for this map when we fix the element G. Okay, and by considering this notation of group action, we will have the following two properties. The first property says that for each fixed group element G in capital G, the sigma g divided by this fixed element is the permutation of the set capital A. And this is why we use the notation sigma g when we define this map. And for the second property, it shows that the map from the group G to SA divided by we map G, the fixed element G, to sigma G. The map is a homomorphism. Here, because according to the first property, we already we can prove that the map sigma G, which is a group action map, is a permutation of A. So this sigma G should inside this symmetric group SA, because it is symmetric group A is the group of all permutations of the set A. And then because according to the definition in above, we know that each sigma G is defined based on one element of the group G. So that is why we have this map from G to symmetric group SA, and this map is defined like this. For each element G in the group, it maps to the group action map defined by this certain element small g, and this map we want to show that it is a homomorphism. Okay, let's begin to prove those two properties. First, we want to show that this sigma g is a permutation. According to the definition of the permutation, it means that the permutation is the bijection from the set A to itself. So we already know that this sigma g is a map from the capital A set to itself, but the only thing left is that we want to show this map is bijection. And to show that a map is bijection, there are two major ways to do that. The first method is to show that this map is one-to-one and onto, and another method is to show that this map has inverse, or specifically this inverse is a two-sided inverse. And the means of two-sided inverse is that like take the, because we are considering the inverse of maps, so the two let's look at what is the two-sided inverse for a map. So for example, if we have a map F, and F maps some element A and to some element some set A to some set B, where here this A does not necessarily be this A in our definition, in our this property, just an example for we want to use here. So this can be any set A. If we have this map, the inverse, the two-sided inverse of F should be like a two-sided inverse should be something like a G map from B to A, and such that we want to have like two cases. First is GF is equal to identity map, and F composite with G is also identity map. The first one shows that the G map is the left inverse map of this F map, and the second case shows that the map G is the right inverse of this F. So if G is both the left side and the right side inverse of F, then G is the two-sided inverse. Okay, so let's prove that there is a two-sided inverse for this sigma G. So for fixed G in the group G, sigma G, we climb sigma, like sigma G inverse is the two-sided inverse of sigma G. Okay, if we climb this sigma G inverse is the two-sided inverse of this sigma G, and if this is true, then this sigma G is a bijection, and then it is a permutation, which is what we want for the first property. Okay, so now we want to show that this sigma G inverse is the two-sided inverse of sigma G, which means this one is the both the left inverse and the right inverse of sigma G. To show that, first we show this is the left inverse. So before that, we want to, for any element A in A, if we consider this GA, so we composite the sigma G inverse on the left side of the sigma G, and what we want to show is that this composition is actually an identity map. If it is identity map, so it satisfies this equality, which means this sigma G inverse is the left inverse of this sigma G. Okay, how can we get the identity map from here? So according to the definition of composition, this part is equal to sigma G inverse map sigma G map A, like this. This is how does the composition of maps work. Then here for this map, because according to our definition for the this sigma G notation, when we map the element A by this sigma G, it is equivalent. It is equal to we use the element G to act on this element. So we get G inverse and G dot A. So the element G act on the element A in the capital A set, and then this is also equal to we use the definition for this sigma notation again. It is G inverse act on the result of G act on A, like this. Okay, and then here, because like those like G and G inverse act on some elements, so we can use a definition of group action at the beginning, which is the first property of group action. So we can see that is equal to we do the multiplication of the two elements from the group, then act on the element. So this equals to G inverse times G act on A, like this. This just this G inverse multiplied by G is just an identity, so we can see that is 1GA, and this, according to the second property of the group action in the definition, this just gives us A. Okay, so now we can see that when we use the composition of sigma G inverse and sigma G to map A, the result is A itself. It means that sigma G inverse composite with sigma G equals identity map, and this means that sigma G inverse is left inverse of sigma G. Okay, so the first this part is done, and then we want to show that it is the sigma G inverse is also the right inverse of sigma G. So similarly, we can consider this sigma G composite with sigma G inverse, then map A is equals to sigma G sigma G inverse A, like this. And then by the definition of this sigma notation, it is equal to sigma G map G inverse act on A, and also it is equal to G act on this one, like this. Just this process is very similar to this first one, so I just go through it very quickly here. So here, by the definition of group action, this is G times G inverse act on A, and this is identity. So identity act on A is A itself. So again, this shows that this part is equals to identity map map, and it means that sigma G inverse is right inverse of sigma G. Okay, now we prove that this sigma G inverse is both the left inverse and the right inverse of sigma G. So sigma G is the two-sided inverse of sigma G. Okay, and because sigma G has a two-sided inverse, it means that sigma G is a bijection. So sigma G is a bijection, and then by the definition of permutation, sigma G is a permutation. And because it maps A to itself, so permutation on A. Okay. The next thing is to show that the second property in which the map from G to SA, the symmetric group on the set A, is the homomorphism. Okay, so to do this, we first let the map to be F, which maps G to the symmetric group SA, by F maps G to sigma G. Just just give a name for this map we want to show to be the homomorphism. Okay, and then for any element G and H in the group, and for any element A in the set A, capital A, because we want to show that this map F is the homomorphism, then that is to show that F G H equals to F G F H. So this is what we want to show. This is want to prove this, and to show that we can do is to use like those maps, the maps on the left hand side and the right hand side of this equality to map any element in A, and if they always equal to each other, then those maps are the same. So let's begin. So we want to do GH, this map the element A to something. This equals to because FGH by the definition of the map, it is sigma GH, like this, and A, and then because by this notation, the definition of this sigma notation, it means the element GH act on the element A, and then by the definition for the group action, this can be considered as G act on H act on A, and then this equals to G act on H act on A is actually sigma H map A. By the this is the due to the definition of group action, and then G act on this one is equal to sigma G map this part. Okay, it's like this, and then because these we have two maps here, and by the definition of the operations of maps, this is just the composition of those two maps, sigma G and sigma H, and map A, and then this sigma are mapped from G by F and mapped from H by F, like this, A. So we get this from this first one, because this is true for any A in the set capital A. So this means that the left hand side FGH equals to FG composite with FH, which is what we want here, because the operation between the maps is the composition. So this is not the regular multiplication between maps. It means the composition of those maps. So this shows that F is homomorphism. Okay, then we finished the proof of those two properties, and that is what I want to talk in this episode. In the future, we will spend a lot of time to talk about many details about group action, and it is very interesting. So let's do that in the future. And thank you for watching. See you next time. Bye.